you for coming on to today's lesson. Whoops, someone else joined in. Who's that then? Hello? Oh no, it's me. Okay, I'm really good at this, as you can tell. Right, so can someone please confirm that on their screen they can now see Unit 5, Solids Under Stress. Can someone just confirm that's on their screen for me?
Yeah.
Brilliant, thank you. Right,
Yeah.
and hopefully you've got your paper copy in front of you. So the first page is just some definitions that you need to know off by heart, right? The words elastic, plastic, strong, stiff, brittle, tough, ductile, and tension and compression, right? And most of them are common sense. I'm not going to read through them verbatim, word for word. You can do that in your own time. But a couple of key things I want to mention. Plastic. A material behaves plastically if it is permanently changed after being deformed, right? Now, I wanted to think of something like a rubber band. And obviously, when you stretch that, it will return to its normal state. But there will come a point where you stretch it too far, and then it's permanently changed or breaks. Okay, and we'll talk about that more in detail. So that in a minute. That's the difference between elastic and plastic. Brittle is a word that you may know from things like peanut butter brittle, and it's a solid that doesn't really bend or stretch at all. It'll just break when a certain amount of pressure is applied to it. And the main example we'll talk about in this unit for brittle is glass, and we'll talk about on a molecular level why glass is brittle. So it doesn't bend or stretch at all. Ductile is a word that may be new to you. If something is ductile, it can be stretched out into another form. We'll talk about that more in a bit. And then these words here, tension and compression, they are the physics terms for stretching and squashing. Okay, so when you stretch something, you are applying a tension to it. And when you squash something, you are applying a compression force to it, right? So you'll need to be au fait with that vocabulary there. And the first thing we're going to look at is how we classify our solids. Again, this is all bookwork. You will be asked to, write this out on your exam, recall this information. So there are 3 classifications of solids that we have in A-level physics: crystalline, amorphous, and polymeric. Okay, and crystalline solids, this is the important stuff here. At the molecular level, the atoms are arranged in a regular way throughout the solid. So that there you need to highlight. Okay, in a crystalline solid, we have a regular lattice of atoms, just like you would have been introduced to atoms in a solid back in year 8. Okay. We say it has short range order and long range order, which means that lattice formation goes pretty much throughout the solid. And examples of crystalline solids are metals and diamond, okay? Because in a metal, the same pattern is repeated over millions of atoms. Now, what I'd like you now to do is go straight onto the next page as well. Here I found a good example in more detail of crystalline solids, and I think I bored you to death with my tale of when I did my physics degree in uni. Cardiff Uni was one of the only unis in Britain that had a scanning tunneling electron microscope, and that would allow us to look at the molecular structure, as you can see in this picture here. And this shows the molecular structure in a piece of gold. And as you can see, it's very tightly bound lattice structure. Something you need to take from this is a characteristic of these crystalline solids is their sharp melting point. So there'll become a moment when the temperature reaches a certain point where it'll instantly go from solid to liquid. Okay, we call that a sharp melting point, and that is a characteristic of crystalline solids, something you need to know, so highlight that. Okay. Another thing I want to mention here is in that diagram there, within that circle there is something called a grain boundary. And you'll need to understand this term, grain boundary. The lattice structure of atoms throughout the crystalline solid is uniform throughout, but there will become a point where there might be a change in angle of those grains of atoms, for example, okay? And that slight deformation there is called a grain boundary. And of course, it is a point of weakness, and we'll talk about that more later, right? So the first classification, crystalline solids, they're your metals, basically. It's an ordered lattice structure. It has a sharp melting point, but where there is some non-uniformity, we call that a grain boundary. Right, now I do have the chat open as well on the screen, I can see it. So if you want to ask any questions as I go along and you don't want to say it out loud, please chuck it in the chat. Right, let's go back now to the page before and talk about what we call amorphous solids. So amorphous solids, again, have a lattice-like structure of atoms, but only in what we call short range. So there's lots of little different structures of lattices along the solid. And the best example of that is glass, okay? As you know, glass is heated sand. So the silica dioxide molecules in glass are bonded regularly over short distances, just tens of molecules. Now we can't even comprehend how small that is. But there's no long range order. So they don't go over millions like they do in crystalline solids. And as a result, amorphous solids are strong in compression, but very brittle. So that means if you apply a tensile or a tension force to them, they will snap, okay? So if you think of glass, you know, glass is very strong, but if you do bend it slightly or try to bend it, it will snap straight away. And that's because the molecules don't have this long range order of lattice structure. So that's your example of amorphous solids. And the last one is your polymeric solids, or your polymers. And I'm sure you've already guessed, that's your carbon-based plastics, as we call them. And these are made up of long chains of molecules, right? So think of rubber and plastic and polythene. Think of your plastic bag from Tesco's. You can pull that apart and stretch it, but there will come a point where you stretch it so far that it doesn't go back to being its normal uniform shape. And that's called a polymeric solid. And the words you might need to replicate on your exam, there's long range order along these molecule chains, okay? So there's chains of molecules, but there is long range disorder between the chains as they are randomly arranged. Now that might sound rather confusing. So the best example we can give is, I'd like you to imagine a plate of spaghetti. And go to your next page again now. And go to the bottom of the next page. And have a look at this middle box here. Here is your disorganized plate of spaghetti. These are your chains of molecules in the polymeric solid. And you can pull, if I pull from left to right or up from down, those chains of spaghetti, those chains of molecules would stretch out to look like this box here, okay? So it does have that order, but of course, before you stretch it out, it's completely disordered. Now that gives it strength. So when you stretch it and you unravel the plate of spaghetti, obviously the length will increase of your solid and it has strength, but there will come a point where you break the bonds in these long stretched chains, and that's when it won't return back to the plate of spaghetti. And that is called plastic deformation, which we will talk about, as we go through this unit. The atoms within the chains are held together by strong covalent bonds, okay? And your best examples are rubber and polythene and other types of stretchy plastic, right? Okay, any questions so far on that? Nothing comes up in the chat, or if you don't say anything, I will move on. Okie dokie. Right, don't worry about the next page. Let's go straight now to page number 4, which is another list of definitions, and we're going to tick them off as we go through the unit. So far, we have discussed crystals and crystalline solids, their molecular structure, their strengths, their weaknesses, the definition of the sharp melting point. We have discussed amorphous solids, given the example of glass and the term brittle, and a polymeric solid, which is your plate of spaghetti, your rubber, your plastic, that can be initially stretched, and as long as you don't reach a certain breaking point, we'll go back to that plate of spaghetti. I also mentioned the word ductile material at the start. So that's a material which can be drawn out into a wire, so you can stretch it and manipulate it so it becomes into the form of a wire. Okay, so there's 5 definitions there that you need to know off by heart. Over on to the next page, please. Let me know if I'm going too fast as well. So we briefly spoke about the grain boundaries. Okay, the grain boundaries in a crystalline solid, and we'll talk about that further probably next lesson. It creates what's known as a dislocation, which creates a breaking point, and there's the bit on grain boundaries. That's the boundaries between the lattice structure in a crystalline solid where maybe the angle of molecules changes. Right, so there's some book work to get us started. So now let's do a little bit of mathematics to go with it. On to your next page, please. All right, I'm missing a page. Right, I'm missing a page. I want us to look at this page here. Do you have this page in your pack, kids, with Hooke's Law? This page here. Can someone say yes or no? Do you have that page? Hello?
I don't think I can see it anywhere.
Okay. And on the back of that page is an empty graph. You don't have that page?
No, I don't have
Okay, no problem. I'll just talk through it and then we'll do the activity after it, okay? So is your next page... Okay, I can see. No problem. Right. Sorry about that. Never mind. So you will have met Hooke's Law at GCSE, I hope. Hooke's Law tells us that there's a proportional relationship to the force applied to a spring and the extension that it produces. So for example, if I put a 1 kilogram weight on a spring, it will extend 10 centimeters, and then if I put a 2 kilogram weight, it would extend 20, 3 kilograms 30, etc., etc. Right? And of course, there'll come a point where you put too much weight on that spring, and the spring won't spring back. It'll just stretch out, and we call that deform, and then that's it. The spring is burst. Okay. Now that relationship can be described mathematically using what we call Hooke's law. So force is proportional to extension, and if you swap that proportionality with an equals k, like we would normally do in mathematics, k is a constant and is called the stiffness constant of that spring. And obviously that would be different for different types of material that would create these springs. Okay. The SI units of K are newtons per meter, because as you can see, K would be the force in newtons divided by the extension in meters. So the SI units are newtons per meter, and it tells you effectively how much force you need to stretch the spring by 1 meter. Don't forget, force is mass times acceleration. So if we're vertically hanging a weight on a spring, it'll be the mass of the spring times gravity 9.81. Right? And we'll look at some questions on that later. Graphically, it's pretty much represented very crudely like this. Okay. So because it's a proportional relationship to start with, it's a straight line graph. Right, so force here going up the y-axis, extension going across the x-axis, and it's a straight line graph because it's proportional. But there will come a point called the limit of proportionality where that straight line ceases to exist and it then becomes a curve. And this is called the elastic limit. This is when that string stretches beyond its limit to go back. and then of course the metal or plastic or whatever it is deforms, and it won't return to that original state. And then finally, of course, whatever the material is, it will snap into two, and that is called the breaking point. Now, mathematically, the importance of this graph is this point here. The value of K, the stiffness constant, is given by the gradient of the graph. Okay, so if you think of y equals mx plus c, going back to year 8 mathematics, we don't have a plus c because the graph starts at 0. No force, no extension. So the y-intercept is at 0. So K is effectively the gradient. If force goes up the y-axis and extension across the x-axis, then K, the stiffness constant, is the gradient of the graph, the change in height divided by the change in length. And you will be, on most exam papers, you will have to calculate the gradient of a graph to find that value of K and then utilize it in a couple of other points in the question. So if you had this sheet, and I can only apologize for not having it, I'll go back to the pupil's copy, of course, which it isn't on. Well done, Richie boy. I would have asked you to have done this exercise here. The table below shows the length of a spring and how it varies when different weights are attached to it, right? So the initial length of the spring is 12 centimeters. And then I add weights going up in 2 newtons each time. And this is the new length of the spring each time. So obviously to get the extension, I need to subtract the new length, take away the original length of 12. So that's how these numbers in red are appearing every time. And I would have wanted you to have done this exercise for me. So I'll repeat that. To get the extension, just subtract 12, the original length, from every new length that a weight is added. And then over the page, I'm going to ask you to plot that graph, okay? So here was your blank sheet that you didn't have. I wanted you to plot a graph of those going up in 2 newtons versus the extension. I wanted you then to determine the limit of proportionality. So that is the point on the graph where the straight line ceases to exist. And then I would have asked you to calculate the stiffness constant up to the limit of proportionality, which is of course the gradient of that graph, right? So being as you can't do it because Sir forgot to give you the right sheet, this is how it would look. I'll just shrink in. So if I was plotting those points, you can see it looks like it should. It's a straight line all the way up to around about there. Then the straight line ceases to exist and it starts to curve, 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 curve. And that would be the breaking point of that material there. Okay, so there's the plotting of the graph. That's something they might ask you to do. Using your graph, work out the limit of proportionality. So I'm sure you'd agree it's around there that it stops being straight, and that's roughly 12 newtons. And then work out the stiffness constant at this limit of proportionality. So here we're working out the gradient. So from here to here, change in height is 12, change in length is 20. You need to be careful here though. The units is in centimeters. So I would have to change that to 0.2 meters. And I get a stiffness constant of 60 newtons per meter. Right, I'm sure you can all do that. And then the last question, an unknown weight is then attached to the spring, and the spring length is measured as 21 centimeters. What is the unknown weight value? And the common error here is, of course, kids go to 21. They go to 21, they'll come up, they'll hit their line, they'll come across, and they'll say, oh, it's about 12 and a half. And they need to remember that you need to find the extension. So if the original length of the spring was 12, the extension is 9. So I'm actually going to go to 9, come across, and it's about 5.2. All right, so it's a very basic exercise that you might get assessed on, and you're going to do one for me in a moment. Sorry that wasn't in your pack. So So let's look at your next page. I believe your next page looks like this. Could someone please confirm your next page is a bit of a blank space and then Hooke's law and a picture of a spring dangling? Can someone say yes? Brilliant. Thank you for that. Now, I've left a little gap up here because I quickly want to talk about what happens if we put two springs together. So, as you will have done with resistors in an electrical circuit, two springs together, one after the other, we would call in series, and two springs together next to each other, we would call in parallel, right? So I'm sure you're aware of those terms. And if you think of it practically, if I do put two springs together in series, it will just double the extension, right? So I've got the stiffness constant of the first spring, the stiffness constant of the second spring, and it would give me double the extension, right? So you need to know that. So the total stiffness constant would be the sum of those two, and the total extension would be 2 times what you would expect. If I put them in parallel, it's the opposite, okay? The total extension now would be half of the expected extension. And like with your resistors, you have to reciprocate the stiffness constants and treat them as fractions. So 1 over the total value of K is 1 over K1 plus 1 over K2. Now, it's a really important concept that is, right? I'm going to say it again, I want to absorb it. If you stick two springs end to end, and let's say they're the same springs, you are going to get double the extension. If you stick two springs together next to each other in parallel, you are going to get half the extension. Graphically, it will look like that. Okay, so here's my normal spring here. Here's my straight line proportional line. Stick them together. I'm going to need more force to produce the extension. Stick them next to each other, and it'll be the opposite. All right, so please be aware of that because you're going to need that in an upcoming question. Now, these notes underneath are just replicating what we've just spoke about, right? Hooke's law says that force is proportional to extension. In an elastic change, the body returns to its original shape and size when the load is removed. There will come a point, though, referred to as the elastic limit, where once you go past that, it's deformed permanently. Now, you'll notice this graph looks different. Our graph went up and curved off to the right, and this graph seems to be going up and curving off to the left. And I'm hoping you've spotted, because they've tried to confuse us and put the axes the other way around. They've put the extension up the y-axis and the force along the x. So be aware they could put either form of that graph on your exam. Okay, either form of the graph could appear on the exam. And just like you will be asked to replicate the definition for conservation of momentum or principle of moments, you could be asked for 1 mark to write down Hooke's law, and provided the elastic limit is not exceeded, the extension is proportional to the applied force or load, right? So learn that off by heart for 1 free mark. Right, so let's go back to your pupil's copy. Now, I know this is a little bit dry, but we'll come up to some questions in a moment. There's Hooke's law repeated again. Now, let's talk about the work and the potential energy stored in springs. So when a material is stretched, you have to obviously use a force or do some work to stretch the material. And that work that you have done is stored in the spring or bit of plastic, let's say spring, as potential energy. Because of course, when you let the load go, it's going to spring back, isn't it, right? So the work done in stretching the material is equal to the amount of potential energy stored within the spring. And this stored energy is called the elastic strain energy. And on the graphs we've just been looking at, on the force extension graphs, This potential energy stored, called the elastic strain energy, is the area under the graph. Now, there's three ways to look at this. Let's go back to this graph that I had earlier. Apologies. Bear with me. This one here. Now, if I'm working out, say, the energy stored from this point on the graph, the area under the graph, as you can see, will always be a triangle. You're not going to want to calculate it after you've reached the limit of proportionality, or the elastic limit. So it's always going to be half the base times the height. Now let's look at the mathematics of that then. Where's it gone? Right. Work done is force times displacement. The force isn't constant though. It rises from 0 to wherever you are taking the measurement. So the average force will be half of that total force. So the work done is half the force times the displacement. Hooke's law means we can swap F for kx. So doing that, I will get a half times kx squared. That is wrong. So I want to correct that, please, on your pack. Okay, this should be the work done is a half times k times x squared. I've written here on my notes, that's explained better on the next page. So before we look at these two questions, go to your next page for me. You've got a picture of Tigger and a picture of a lady doing some exercise. And let's look at it here. Work done is average force times extension. Average force going from 0 to F is a half F. So the work done is a half times F times X. Substituting in F equals Kx will give you a half Kx squared. A half the base times the height. That's the area under the graph. Okay? You're going to need to know that, and you're going to need to practice those calculations. So going back to the last page, very, very quickly, this will only take you 60 seconds tops. Have a look at these two questions here. An elastic cord has an unextended length of 25. When the cord is extended by applying a force, the length becomes 40. So straight away you can work out the extension. It gives you the value of the force used, 0.75 newtons. Calculate the elastic constant K of that cord. Now be careful here because your extension is in centimeters, so you need to change that to meters. And then the second one, calculate the elastic constant K. They give you the extension and they give you a load. Again, just be very careful with the units. Make sure you change that to meters. So can you quickly do those two divisions for me and say done it in the chat when you have, please? Anybody still there? Anybody got those answers then? Can you just put a yes in the chat for me so I know to move on? Thank you, Pat. Right. So you should have had for the first one, the extension was 15 centimeters. Put that into meters straight away because the SI units of K newtons per meter. They told us the force was 0.75. Chuck the numbers in your calculator, you get 5 newtons per meter. The second one, the extension was 3.5 centimeters, which is 0.035 meters. They gave us the force, so the value of K, the stiffness constant for that material, was 400 newtons per meter. Okay, all okay there, I trust? Right, so now I wanted to go over 2 pages. Thank you, Al. And you are going to have a look at an exam question for me. I'll talk you through it all first, right? But then I am going to want you to do it properly. So this was off the exam 6 years ago. There is a force extension graph, right? The following graph shows how the length of a spring varies with the applied force. Hooke's law is obeyed throughout. So it's a straight line, so it hasn't reached the elastic limit for this particular spring. For 1 mark, state Hooke's law, right? So you can write that down. For another mark, determine the spring's unstretched length. So that will obviously be that value there because there's no force applied at that point. And then it starts getting all physicsy. The spring is used in a simple accelerometer, which is a device for measuring acceleration. Straight away now, I hope your brain's going, acceleration. What do I know about that? Force equals mass times acceleration. The spring is attached to a 0.4 kilogram mass, which is placed on a friction-free surface as shown, and the device is installed in a car. The car accelerates uniformly from rest. During the acceleration, the spring is extended by 12 centimeters. Use this information and the graph to calculate the car's acceleration. Right. Now, if you're thinking SUVATs, V equals U plus AT, don't bother because time isn't mentioned at all. So because they've given us a mass and we want acceleration, we're going to look at F equals ma. Okay, great. So if I could work out F, because I know the mass, I could then get the acceleration. Now, how can I get the value of F? Well, let's go back to here. F equals K times X. And they've told us that the extension X is 12 centimeters. So if I can find the value of K, the stiffness constant, I can times it by 12 and get the value of F. How do I get K? Well, I'm sure you'll remember. K is the gradient of this graph here. So this is the maths you're going to have to do. You're going to have to find the gradient of this graph first to get the value of K. Once you've got the value of K, you can use Hooke's law, F equals Kx, to get the value of F. Once you've got the value of F, you can use F equals ma, because you know the mass, to get the acceleration. Now that might sound a lot of work for 2 marks, but you're only using 2 equations and working out the gradient. So hopefully you're halfway through it. I'll give you 90 seconds when you think you've got an answer for me. And it's a reasonably normal looking answer. When you think you've got an answer for me, just please type in the chat, done it. Okay, off you go. Are we looking? Anybody got an answer out yet? Okay, sorry Al. You know I always go too fast. Thank you, Pat. Are you looking at your answer and thinking, yeah, that looks reasonable? It's not like the square root of pi all to the power of x. Cool. Shannon, are you still there, or are you watching Homes Under the Hammer? Tell the truth. And watching Homes Under the Hammer. I like it.
No.
Multitasking. I'll give you 30 seconds and then we'll go through it. Brill, thanks Al. Okay, so state Hooke's law. The tension in a spring or wire is directly proportional to its extension, provided the elastic limit is not reached. You have to have that last bit to get that mark, right? Determine the spring's unstretched length. So that was this point here, because there's no force applied, and it was 4 centimeters. Right. And then they asked us to work out the acceleration. So as I said, we had to get k first. Now you can pick any 2 points on a straight line to get the gradient, but I've always tried to encourage you to pick 2 relatively easy points. So I picked here and here because the length there is 10 and the height there was 0.5. So my gradient was 0.5 divided by 0.10. Don't forget, units were in centimeters, and the SI units of K are newtons per meter. So it was 0.5 divided by 0.1, which was 5 newtons per meter. Once I knew that value of K, then I could use Hooke's law, F equals Kx, to determine the force. It told me the extension was 12 centimeters. So I did 5 times 0.12. Don't forget, you have to put it in meters, which gave me a force of 0.6 newtons. Then I could use F equals ma, rearrange it. A is F over m. The force was 0.6. My mass, they told me, was 0.4 kilograms. 6 divided by 4 is 1.5. So the answer was 1.5 meters per second squared. Anybody get that? Yay, well done. That's awesome, Pat. Well done. Yay, well done, Al, and I bet you fit in. Brilliant. Right, now let's look at the next part. Shannon, did you get that idea? Come on, you're the only one who haven't said yes. Just fib and say yes, like Ellie did. Fine.
Yeah.
Yay, well done. Right, now let's look at the next part. Okay. Now the next part, all of that there was only worth 4 marks, and the next part is worth 7 marks, right? And here we're talking about the elastic potential energy stored in the spring, right? So first of all, they're asking when the car's acceleration is the same as in B, right? So we've worked out here, we've worked out our answer for B. We know what the acceleration is. Now don't forget, there's a couple of ways to work this out. You can either use energy is a half k times x squared, or you can work out the area under the graph, right? So you have 2 options there, obviously, or you could use a half times f times x. There's 3 options. So using either of those options, work out the car's acceleration, right? And then they ask you to calculate the energy stored when the car travels at a constant velocity. And this time it says explain your answer. So this obviously has got a bit of explain to do. This one's just a mathematical one, chucking your numbers to an equation or find the area under the graph. Here you have to explain your answer. And of course, I'm hoping you've picked it up already. If the car is traveling at constant velocity, then something must be something. And you can go from there. Don't want to give away the answer, right? I want to think about it yourself. And then finally, the accelerometer is now modified by attaching a second identical spring as shown. Now they're not stuck end to end, they're stuck next to each other. So if you remember what I spoke about 10 minutes ago, when they're next to each other, the extension will halve, right? Oops, I think I just gave you half the answer. So explain the effect that adding the second spring has on the extension. You've got that for free. And then knowing that the extension is halved, what effect does that have on the total elastic potential energy? Don't forget that elastic potential energy is represented by the equation a half kx squared. So if the extension is halved, what happens to the total potential energy? I'm going to give you just 2 minutes to scribble down some answers for that. You'll probably get more out of it just looking at my answers as well, because it's the first time you've seen anything like it. But try and scribble down some answers for those, and then we'll go through it, and then we'll pretty much be done for the day, right? Have a crack. Off you go. Right, shall I go through it?
Yeah.
Okay, thank you. Right, here's what I've got. So calculate the elastic potential energy. Don't forget, that's another way of saying calculate the work done in stretching that spring, right? So it's being stretched, and obviously it then contains potential energy. So you have three options. You can either use a half times kx squared, which is the same as a half fx, because don't forget, f equals kx. That's why those two are the same. But if you don't have some information, you might sometimes have to use the fact that that's the area under the graph. Half the base times the height. Don't forget, the base is the extension, the height is force. Half the base times the height. Either of those, if you chucked in the right numbers or did the right area calculation, hopefully you got out 0.036. We are calculating an energy, so the unit is joules. All right, I imagine if they were strict and you didn't put joules, you could have been docked a mark. All right, calculate the energy when the car travels at a constant velocity. Well, if the answer is 0 joules. Right, there's no energy in the spring if it's traveling at a constant velocity, because at a constant velocity, acceleration is 0. And then thinking of F equals ma, if a is 0, F must be 0. And as the energy stored is a half times F times X, if F is 0, there is no energy stored. So that's how you got the 2 marks there. And then the last one, they put 2 springs in parallel next to each other, right? So as I told you, you just need to know now that that means you have a resultant of half the extension on each. So that was the first mark. So the total extension would be half. But if you go back to this equation here, because the total energy is half times the stiffness constant times the extension squared, the extension squared is a quarter. So the actual total elastic potential energy stored in the spring would be a quarter of the original value, coming from a half kx squared. Okay, did anybody get anywhere near those sort of answers? Oh, just fib and say yes. Kind of. Well, I'll take that for your first go. Thank you, Al. Right, so we're looking at, what's this, 7, there's 11 marks there. Right, 11 marks on an 80-mark paper. And they're pretty attainable marks, those 11. And obviously there's a lot more to this unit yet to come. If we was in school now, this is a double lesson, we'd now go on to the next part, which is called the Young's modulus. But we're not going to do that now because we're all a bit fried, screen time, etc., etc. So let's just very quickly before we leave, just look at the last page. All right, and I'll go through it with you. So as a summary about, so we know what Hooke's law is now, F equals kx. We know that k is the gradient of the force extension graph. We know that the graph curves off at the end when you reach the elastic limit. We know that the energy stored in the spring is equivalent to the work done in stretching it, and it's either a half fx, a half kx squared, or the area under the graph, right? So that's everything we've learned today, which may be new to you. And then the last, excuse my scribbles, the last example I would have asked you to have done, but I'm not going to, is work out the energy stored in that very first example that you didn't have in your pack, right? When the unknown weight was attached. And if you remember, we worked out the unknown weight was 5.2 newtons, and the extension it produced was 9 centimeters. So I could have used either a half fx or a half kx squared or the area under the graph, and it came out as 0.23 joules. So that's it for today, right? The next time I see you, which we'll have to arrange, we will be looking at the main sort of body really of this unit, which is working out something called the Young's modulus, which is like a universal stiffness constant for a certain type of material. It's quite mathematical, but I know you can handle it. So don't lose this pack, and you will get another one in the post soon. I'm going to request that our next live lesson is either next Monday or Tuesday. So I'll give you plenty of notice, and you can let me know if you can attend or not. So are there any questions or comments to finish with? Anybody?
I don't think so.
Well, rightio then. So I haven't got a clue what day it is. Enjoy your weekend if it's Friday. If it isn't, enjoy whatever day it is. And I'll see you next time, right? Keep an eye on the chat. I know Daki's already posted something today. If you have any questions, just email us or put us on the Google Classroom, and I will always respond as soon as I can. All right, thanks
you.
everybody.
Bye.
See you soon, and ta-da.